We'll now learn how the confidence interval that we studied in sampling and in distributions can also be used to conduct a hypothesis test. So using bond portfolio data from the previous examples, construct a 95% confidence interval for the population mean daily return over the 360-day sample period, use a Z distribution, decide if hypothesis mu equal to 0 should be rejected. So just to recall, the mean came out to be 0.05. The standard deviation was given to be 0.16. That was a sample standard deviation. And the standard error could have been calculated as 0.16 divided by square root of 360. So the 95% confidence level around the mean 0.05 would be 0.05 plus 1.96 into 0.6 divided by square root of 360 and 0.05 minus 1.96 into 0.16 upon square root of 360. So that's the 95% confidence interval. Please note, for a two-tailed 95% confidence level, two-tailed because mu equal to 0 is the null hypothesis. We will leave 2.5% on either side. So it will be the same as a 97.5% one-tailed test, which has a critical level of 1.96. So when we compute the confidence level, we can easily do this on the calculator. So with a mean of 0.05, the 95% confidence level comes between 0.0334 and 0.06652. That is, 95% of the times, if the mean has come out to be 0.05, then the value should lie within 0.0334 or 0.06652. Does mu equal to 0 fall in this range? Does the hypothesis of 0 fall in this range? 0 is outside the range. Hence, we can reject the null hypothesis that we already did from our regular test, that mu is equal to 0. You don't need to know this test. You can do the hypothesis test like you always did. However, this is another way of conducting the hypothesis test, and that is, if the hypothesized value does not fall in the confidence interval, then also the null can be rejected or the hypothesis can be rejected. So we studied the t-distribution earlier. Theory says that we should use the t-test if the population variance is unknown and if the sample size is large, or when the sample size is less than 30 but the distribution of the population is normal or approximately normal. In both these circumstances we studied earlier, we should use the t-distribution or the t-statistic. The t-statistic is calculated in the exact same manner, that is the observed mean minus the hypothesized mean upon the standard error. However, the critical value to decide whether or not to reject the null will now have to be looked up from the t-table. If it comes in the exam, the critical value will be provided to you. You don't have to remember the critical values, but just remember the process of conducting the test is similar to the Z test, only the t-table has to be used for the critical values. And you should use a t-distribution when the sample is small and population is normal, or when population is not normal or the population variance is unknown and the sample size is greater than 30. We've studied the Z test. We've conducted 2 Z tests in the previous slides. Please remember, that with a 90% confidence or a 10% level of significance, for a two-tailed test, the critical value is 1.645. For a one-tailed test, the critical value is 1.28. For a 95% level of significance, for a two-tailed test, the value is 1.96. For a one-tailed test, it will be the same as a 90% two-tailed test, because there also we will leave 5% on one side. So it will be the same as a 95% one-tailed test, that is 1.65. For a 99% two-tailed test, the critical value is 2.58. For a 99% one-tailed test, the critical value is 2.33. Let's do one last example and cement the concept of conducting a Z-test or a hypothesis test. In a plant where the sheeting machine is working properly, the mean length of sheets is 5 inches. However, at certain events, the machine gets out of alignment and produces sheets that are either too long or too short. In such a case, the manufacturing is halted to adjust the machine. The machine output is verified every day to maintain quality, for which the quality assurance department takes a sheet sample each day. Today, a random sample of 50 sheets showed a mean length of 49 inches, rather 4.9 inches. The population standard deviation is known to be 0.2 inches. Using a 1% significance level, determine if the machine should be shut down and adjusted. Or please understand that the machine should be shut down if the length is different from 5 inches. So we want to test if the mean length is different from 5. So let's do it. Step 1 is to state the hypothesis. The hypothesis is, or we want to test if the length is different from 5. So the null hypothesis will be that the mean is equal to 5, and the alternative will be that the mean is different from 5. We want to determine if the machine should be shut down and adjusted. We will shut down if the mean length is different from 5. We want to test that the mean length is different from 5. So the null hypothesis will be the other way around. It is what we have to reject. That is, the mean is equal to 5, and hence we will imply the alternative, the mean is different from 5. Remember, the equal to sign will always come with the null hypothesis. Step 2 is to select the test statistic. So we will use the Z-test since it is a hypothesis on the mean and the sample size is greater than 30. Step 3 is specify the level of significance that is given to be 1%, or the confidence level is given to be 99%. Step 4 is to state the decision criteria. It's a two-tailed test. So for the 99% two-tailed test, if test statistic is greater than 2.58 or lesser than minus 2.58, then we should reject the null. Step 5 is collect sample and calculate the test statistic. So the test statistic can be calculated as the observed value, that is 4.9, minus the hypothesized value, that is 5, divided by the standard error, that is 0.2 divided by square root of 50, which comes out to be approximately minus 3.54. Step 6 is to make a decision about the test, as minus 3.54 is lesser than minus 2.58. Reject the null. So if we reject the null hypothesis, that means we reject the statement that the mean is equal to 5 and conclude the alternative, that is, the mean is different from 5. So step 7 would be to shut down the machine. So in this example, the mean length came out to be 4.9 and we rejected the null and we shut down the machine. Now, is it possible that the machine was fine? When the technicians came and they checked, they found there was no problem with the alignment. They had to do nothing. So we conducted a hypothesis test. We rejected the null and we shut down the machine. Is it possible that actually the machine was fine? It was just this sample of 50 that was slightly digressing. If I took any other sample, or if I took a larger sample, the value was in line with 5 inches. Is it possible? If that happens, that is called a type 1 error. That is rejecting a true null hypothesis. The mistake we have done is we rejected the null, that it was equal to 0. So we rejected a true null hypothesis. If actually the machine was wrong or the machine was out of alignment, then it was the correct decision. We rejected and the null hypothesis was false. So then it was the right thing to do. The other way around is also possible. Let's assume in a similar situation, the critical value came out to be 2.2 units and we failed to reject the null and we did not shut down the machine. But actually the machine was out of alignment. As I saw the products in the coming days, they were all different from 5 inches. So actually the machine was out of alignment, but it's just that that sample of 50 did not have many deviant values, and hence we failed to reject the null that mu is equal to 5. That is also an error. It was an incorrect null hypothesis that we failed to reject. That is called a type 2 error. Failing to reject an incorrect null hypothesis. Type 1 error is when we rejected a true null hypothesis because of luck, because of just this sample. It's nobody's mistake. It's just that the sample we took didn't have so many stray values or had extra stray values. Now, as we increase the level of significance, or rather as we increase the confidence level and decrease the level of significance, the probability of a type 1 error starts to go down. Because type 1 error happens when you reject a true null hypothesis. If the level of significance is 1%, that is 0.5% this side, 0.5% on the left, then how many times are we actually rejecting the null? Only 1% of the times. 99% of the times we are anyways failing to reject. The rejection region is only 1%. So the probability of rejecting a true null hypothesis is only 1%, because we are rejecting only 1% of the times. With a 95% level of significance, we are rejecting 5% of the times. 2.5% on the right and 2.5% on the left. The rejection region is 5%. So 5% of the times we are rejecting the null, or the probability of a type 1 error, that is rejecting a correct null hypothesis, is only 5%. So the probability of a type 1 error is equal to the level of significance. The problem, however, is that if I keep the level of significance too small, let's say I make it 1%, then it automatically will increase the probability of a type 2 error. Type 2 error is the error that you failed to reject an incorrect null hypothesis. If my rejection region is just 1%, that means in most of the cases I'm failing to reject the null hypothesis, or the value has to be really extreme for me to reject it. So is it possible that the machine was actually out of alignment, but I did not reject the null hypothesis because my level of significance was so low? So even with very extreme values, I did not reject because I wanted to reduce the probability of a type 1 error, that is rejecting a true null hypothesis. I ended up committing a type 2 error, that is failing to reject an incorrect null hypothesis. So please note, there is no way to reduce the probability of both errors unless by increasing the sample size. If you increase the sample size, that is the only way you can reduce the probabilities of both errors. Otherwise, as you decrease the probability of one error, you will increase the probability of the second error. The power of a test is calculated as 1 minus the probability of a type 2 error. The probability of a type 2 error cannot be as easily calculated as the probability of a type 1 error, which is simply equal to the level of significance. Decreasing the probability of a type 1 error by reducing the level of significance will increase the probability of a type 2 error, or reduce the power of the test, which is 1 minus the probability of a type 2 error. Probability of a type 2 error can be independently reduced only by increasing the sample size. Otherwise, as you increase the probability of one, you will reduce the probability of another, and vice versa. Another important concept is that of the p-value. So the p-value is defined as the probability of obtaining a test statistic that would lead to a rejection of the null hypothesis. Never mind the first definition. Remember the second definition, that the p-value is the minimum level of significance for which the null can be rejected. For example, if we calculated our test statistic and the test statistic came out to be 1.97 and it was a two-tailed test, so in a two-tailed test, if the test statistic came out to be 1.97, then at a 99% level of significance, can I reject the null? To reject the null, the test statistic has to be greater than the critical value. Only then we reject it. So the test statistic, that is observed value minus the hypothesized value upon the standard error, for example, comes out to be 1.97. So with the 99% level of significance, where I leave 0.5% here and 0.5 on the left, critical value is 2.58, I cannot reject the null. With the 97.5% level of significance, can I reject the null? Again, we'll have to leave 1.25 on this side and 1.25 on the other. If the level of significance was actually 95%, 95% implies 2.5% on the right and 2.5% on the left. Remember, the critical value for a 95% two-tailed test comes out to be 1.96. For a 95% one-tailed test, it is 1.645. So for a 95% confidence, would I be able to reject this null? Or if the level of significance was equal to 5%, would I be able to reject the null for a two-tailed test? So the p-value in this case would be 5%. This is the minimum level of significance at which the null can be rejected. If the p-value was 10%, or rather if the level of significance was 10% or anything greater than 5%, then critical values would again have been lower, 1.645, and I would be able to reject the null. So if I can reject it for 5%, then for 6, 7, 8, 9, anything greater than 5, also the null can be rejected. So p-value is the minimum level of significance at which the null can be rejected. Now the question is that if it is a two-tailed test and the test statistic comes out to be 1.55 instead of 1.96, the test statistic now comes out to be 1.55. Calculate the p-value, or calculate the minimum level of significance at which the null can be rejected. It's a two-tailed test. T statistic is given to be 1.55. You may need help of the table. Okay guys, don't worry, understand it once again, it's pretty straightforward. P-value is the minimum level of significance at which the null can be rejected. Now, with a 5% level of significance, I need the test statistic to be 1.96 or greater to be able to reject it. With a 99% level of significance or confidence level or 1% level of significance, I need the test statistic to be 2.58 or greater to be able to reject the null. If 1.55 is the test statistic, so the calculated value has come out to be 1.55. What is that confidence level and what is that level of significance at which even a 1.55 value will get rejected? That means, how much should I leave on this side such that I reach a critical value of 1.55? So if we look at the cumulative Z table, that will tell us that how much is left on the right hand side for a given Z value. If we enter Z as 1.55, it will tell us the area of the black shaded region, that is how much belongs to the left, and we can easily calculate how much belongs to the right by doing 1 minus this. So for 1.55, 0, 1, 2, 3, 4, 5, 93.94% of the total values lie to the left of this value, or 6.06% of the values lie to the right. That means from the right hand side, I need to leave 6.06%. If it was a one-tailed test, this would have been the answer. That is the level of significance of 6.06%, then you can reject the null for anything greater than this. But the question is a two-tailed test. In a two-tailed test, when will I leave 6.06% on the right hand side? When my actual level of significance is twice of this, that is 12.12%. For a 5%, I left 2.5 on either side. For a 12.12% level of significance, I will leave 6.06% on the right and 6.06% on the left. So the minimum level of significance at which the null can be rejected is 12.12% if this is a two-tailed test. In the question, if the level of significance is 5%, so in the question, if the p-value is given and the level of significance is given, then the hypothesis test is done. We don't need to compute the critical value. If the level of significance is 5%, then can this null be rejected? Let's solve the regular way. If level of significance is 5%, then the critical value needed is 1.96. What is our value? 1.55. So can we reject the null? No, because it has to be more extreme for us to be able to reject the null. Similarly, we could have answered this from the p-value. P-value comes out to be 12.12%. The minimum level needed to reject the null is 12.12%. What is the level of significance in the question? Only 5%. So can we reject the null? No. P-value is the minimum level of significance needed to reject the null hypothesis. If the p-value came to be 2.14%, that is, the level of significance needed to reject the null is 2.14%. In the question, if the level of significance is 5%, then can we reject the null? Yes, because minimum level of significance needed is 2.14%. Even if we have 2.5%, that means the critical value will be less than the observed test statistic and the null can be rejected. Given the following regression results, we don't have to study regression. Determine which regression parameters for the independent variables are statistically significantly different from 0 at the 5% significance level, assuming the sample size is 50. So we are asked to test if the coefficient is different from 0. So the null hypothesis would have been that each of the terms are equal to 0. If we reject the null hypothesis, we will conclude that it is statistically different from 0. Now, we are given a lot of information that could have otherwise been used to solve this question. But fortunately in the table, we are also given the p-value. If the p-value is given, the question is solved. The p-value is defined as the minimum level of significance at which this null can be rejected. The minimum level of significance at which this null can be rejected is 45% or 0.45. So at 45% level of significance, I can reject the null. What is our level of significance in the question? 5%. So we cannot reject this null. Hence, intercept is not statistically different from 0. The minimum level of significance required to reject the second null is 0.03%. This value is so extreme, it's very easy to reject it. It doesn't matter. So we only need 0.03% level of significance to be able to reject this null. The question has a level of significance of 5%. So we can reject this null. Hence, intercept is different from 0. We can reject the null. Similarly, x2, we need 5.07% minimum to reject the null. The level of significance in the question is only 5%. So we cannot reject the null that it is different or it is equal to 0. So it is not different from 0. Here we need only 0.15%. Our level of significance is 5%. Hence we can reject this null. So if we reject this null, then we will conclude that this is significantly different from 0. So x1 and x3 can be rejected. The null can be rejected that they are equal to 0. or we will conclude that they are statistically different from 0. So once again, the observed test statistic comes out to be equal to 1.38. Question asked is, if it is a one-tailed test, what is the p-value? So please note, now we are working the other way around. The test statistic has been first computed, and we are then calculating what is the level of significance at which we can reject the null. Please solve. So if the test statistic has come out to be 1.38, that means our critical value must be less than this so as to be able to reject the null. If the critical value has to be 1.38, that means on the left, how much area do I have to leave? It will come to me from the cumulative Z table. So let's look at 1.38. That will be 91.62%. Or 91.62 has to be left on the left hand side, or 8.38% has to be left on the right hand side. If this was a one-tailed test, then all the significance level is entirely anyways left on the right hand side or on one side. So the level of significance has to be 8.38% for a one-tailed test. If it was a two-tailed test, then we would simply double it so that we leave so much region on the one side. In the question, if the level of significance given is higher than the p-value, then the null can be rejected. If it is lower than the p-value, then the null cannot be rejected. This covers the review on hypothesis testing. There are certain other tests that can also be done. We don't need to memorize these values. We don't need to do these tests. Just know that what test statistic is needed and what is the method of performing the tests and the hypothesis. So the hypothesis could be of equality of population means. So our hypothesis is that two populations have the same mean. The average age of CFA candidates is the same as the average age of FRM candidates. Can I make that statement? Yes, I can. So to test such hypotheses, we need to conduct a t-test which has the following test statistic. That is, we will take two samples, one from the CFA population, one from the FRM population, calculate the means of both samples. Hypothesis is that the means are the same, or mu1 minus mu2 is 0. So this is how we can calculate the test statistic. You do not need to remember the formula. The procedure of hypothesis testing remains the same. Only thing, we will now use a t distribution or a t statistic, and the calculation of the test statistic will differ slightly. This is the formula that needs to be applied when variance is unknown but is assumed to be equal for both populations. If we just memorize this. If the variance of the two samples is unknown and assumed to be unequal, then the formula differs slightly. Instead of SP, we will separately conduct S1 and S2 and then apply it. So you don't have to remember these formulae again. Just know that the test can be done, and it will be slightly different whether or not the variance is assumed to be the same or variance is assumed to be unequal. We can simply do a paired comparisons test also. So this test is done to test the hypothesis that the paired differences between two populations are equal to 0. That is, if x1, x2, x3, x4 are the values of the first population and y1, y2, y3, y4 are the values of the second population, then the average of the difference x1 minus y1, x2 minus y2, x3 minus y3, these differences have an average value equal to 0. Or the mean of the population paired differences is equal to a hypothesized value, commonly 0. This test again is a t-tailed test. The samples are assumed to be dependent on one another and the distributions are assumed to be normal. We can similarly structure a one-tailed test also. This will again be a t-tailed test with a test statistic calculated as shown. You do not need to remember the values again, but just know that this is also a test that can be done at times. That is, the paired differences have an average value equal to 0 or have an average value equal to 2 units or 4 units. An important test that may need to get conducted and that we may need to do is the chi-square test. So just like we hypothesized that the mean is equal to 40 or the mean is equal to 5 or the mean is equal to 0, we can make similar hypotheses about the variance as well. So the variance is seen to be following a chi-square distribution, that is a positively skewed distribution, and the test statistic is checked against the chi-square table, or the critical values come from the chi-square table. So the null hypothesis is that the variance is equal to something, and the alternative hypothesis is that the variance is different from that number. Similarly, we can have one-tailed tests or for checking less than or equal to or greater than or equal to in the null hypothesis. The chi-square test statistic you have to memorize can be tested is n minus 1 into s square upon sigma naught square, where n is the size of the sample, s square is the variance of the sample, and sigma naught square is the hypothesized value of the population variance. If this test statistic is within the critical values, then we cannot reject the null. If it is outside the critical values, then we will reject the null that the variance is equal to the hypothesized value, and we will conclude that it is not equal to that value. The critical values for this test will come from the chi-square table. The chi-square distribution has a shape as shown. So since it's a variance, it can never go below 0. Variance will always be positive. It is a square. So it's a positively squared distribution. Degrees of freedom are given as n minus 1, and critical values can be derived from the chi-square table. So 2.5% on the left, 2.5% on the right. The table will give us these values. Historically, ABC Equity Fund has advertised that its monthly returns have a standard deviation equal to 5%. This was based on estimates from 2000 to 2010 period. ABC wants to verify whether this claim still adequately describes the standard deviation of the fund's returns. ABC collected monthly returns for the 36-month period between 2010 and 13 and measured a standard deviation of monthly returns of 4.5%. Determine if the more recent standard deviation is different from the advertised standard deviation. Critical chi-square values are between 11 and 38.5. The procedure for hypothesis testing remains the same. Only the critical value will come from the chi-square table that is given, and the test statistic for a chi-square test will be given as chi-square is n minus 1 into the observed variance upon the hypothesized variance. Please conduct the test. Step 1 again is to state the hypothesis. So the null hypothesis will be that the variance is equal to 25, and the alternative hypothesis will be that the variance is different from 25. The standard deviation is 5, variance will be square of the standard deviation. Second step is to select the test statistic, which in this case will be the chi-square test or the chi-square statistic that we will use. Step 3 is to specify the level of significance that is given to be 5%. So it's not given, but the critical values are given. So alpha, let's assume, is 5%. Step 4 is to determine the critical value. So for a chi-square test with 36 minus 1, 35 degrees of freedom and a 5% level of significance, the critical values come out to be 11 and 38.5. So if the test statistic is less than 11, or if it is greater than 38.5, then we will reject the null. Step 5 is to calculate the test statistic, that is n minus 1 into s square upon sigma naught square, which will be 35 into 4.5 square, which is the observed standard deviation, upon 5 square, which comes out to be 28.35. So can we reject the null? As 28.35 is lesser than 38.5, cannot reject null, or we fail to conclude with a 95% confidence that the hypothesized standard deviation or the population standard deviation is different from 25. We cannot say with a 95% confidence that the variance of the population is different from 25. If we were able to reject the null, we would have been able to say the same. Finally, just like we hypothesized that the means of the two populations should be the same, we can hypothesize that the variance of the population of CFA and FRM candidates is the same. So this will be the test for the equality of variance of two populations. This is also an important test. It is an F test, that is, it follows the F distribution, which is also a positively skewed distribution, and has a test statistic as S1 square upon S2 square. So we are hypothesizing that, or the null hypothesis is that the two populations have the same variance. So we will compute two samples, calculate the variances of the two samples, and compute the F statistic. If we can reject the F statistic, we will conclude that the variance is different. If we are unable to reject, then we will conclude that we cannot with confidence say that they are not the same. Again, questions may not come on these other tests, but you should still know a little bit about the theory. Definitely the first part of today's review is a lot more important. The p-value, type 1, type 2 error, the 7-step procedure is much more important to understand. So that was about the review on hypothesis testing, another important topic and a slightly difficult topic. So make sure you watch the video again and you practice as much as is needed to master the concept. Thanks a lot and see you next time.